Hi everyone, I am Dr. Kushal Roy, Assistant Professor of Mathematics of Dr. B.Tech Engineering College, Durgapur. Today's topic of presentation is derivative of complex functions and analyticity. The outline of my presentation is introduction, harmonic function, harmonic conjugate, Milne-Thomson method for construction of an analytic function, power series and its radius of convergence, some properties of power series, analytic function and its power series representation, and conclusion. So today's topic is complex differentiation and analytic function, which is an important area of mathematics, especially in complex analysis. Also, it is important in engineering branch. We first define analyticity and then discuss several important properties of an analytic function. There is no concept of analytic function in the set of reals, and through the introduction of analyticity in the set of complex numbers, mathematicians added several new properties to complex functions. Complex analysis is included in all streams of B.Tech second semester syllabus of Dr. B.Tech Engineering College, Durgapur in semester 2. Course name is Mathematics 2, course code is M202. So complex analysis included in module 4, which is complex analysis 1, and in module 5, which is complex analysis 2. So let us first define harmonic function. A function psi, which is defined from R2 to R, is said to be harmonic if it satisfies Laplace equation. This nabla square psi is 0. Nabla square psi is what? It is the sum of the second order partial differentiations of psi with respect to x and y respectively. So next theorem, let B be a domain of C, that means it is an open connected subset of C, and let f from D to C be a function such that fz is equal to u plus iv, where u is a function of x comma y, v is another function of x comma y, that means u and v are two variable functions, where x and y are taken from the real part of z and complex part of z. And let us consider f to be analytic, then both u and v are harmonic functions. Next definition is harmonic conjugate. A function psi, which is defined from R2 to R, is said to be harmonic conjugate of a function phi, which is also a function from R2 to R in some domains D of C, if both of them are harmonic functions, and also this fz equal to phi of xy plus I phi of xy is analytic. The function u xy, which is defined as half of log x square plus y square for z equal to x plus iy not equal to 0, has no harmonic conjugate. Actually, you can't have any function v which satisfies Cauchy-Riemann equations with u. Actually, if we want to find some harmonic conjugate of u, in that case we have to find a function v so that u plus iv is analytic. Now, the necessary condition of u plus iv to be analytic is that u and v are harmonic conjugates of each other, and also they are actually satisfying Cauchy-Riemann equations, and they are harmonic functions. So now, actually, what happens here? We can't have any function v which is satisfying Cauchy-Riemann equations with u, and therefore u has no harmonic conjugate. There are harmonic functions which cannot be harmonic conjugate to each other. Let u xy equal to x and v xy equal to minus y. So in that case, both of the functions are harmonic, but they are not harmonic conjugate to each other, since fz equal to z bar is not analytic in C. Actually, sometimes in some books, mathematics books, so the harmonic conjugates are defined as u and v are two harmonic functions, are called harmonic conjugates of each other if they are satisfying Cauchy-Riemann equations. But it is totally wrong. Actually, if two functions are harmonic functions, in that case they can't form a harmonic conjugate of each other if they are not forming any analytic function. Okay, so in a simply connected domain, every harmonic function has a harmonic conjugate. It is very important. Actually, in simply connected domain means it is a connected domain where each and every closed curve is homotopic to zero. That means any closed curve uh, can be shrinked to a point. Okay, so this type of actually domain are called simply connected. There is another definition of simply connected domain. Actually, if a domain, if you are considering any domain, okay, it is called simply connected domain if its conjugate, okay, if its conjugate is another domain. Okay, so it is if it's actually complements, no, sorry, not conjugate, it's complement. If its complement is containing infinity and it's also domain. Okay, so in that case, it is called simply connected domain. So if a function f, which is u plus iv, it is called analytic. Okay, if a function fz where f is analytic, then the derivative of f in any point z equal to x plus iy is f dash z is ux plus ivx. Okay, and it is also defined as uh, he actually it is also defined as that um, since u and v are harmonic conjugates of each other, in that case, you can write ux equal to vy and uy equal to minus vx. So therefore, you can easily substitute those functions, um, those actually relations in f dash z. Okay, so that means f dash z is ux plus ivy. It is actually also it is Vy minus Iui. It can be also written as Ux minus Iui, and also it is Vy plus Ivx. So you can actually have uh, these four forms for the actually differentiation of f at some point z. Now, Milne-Thomson method for construction of an analytic function. If a harmonic function u is known, then we can find the harmonic conjugate of f, and thus we can form an analytic function in a simply connected domain. So how can we form it? So if you are given any harmonic function u, so let us first find ux and uy. In that case, f dash z must be ux minus iuy. So let us consider it to be this gamma 1 xy minus I into this gamma 1 xy, gamma 2 xy. So actually, we are considering ux as a function gamma 1 and uy as a function of gamma 2. Now, if we put x equal to z and y equal to 0, then we are getting f dash z equal to gamma 1 z comma 0 minus I gamma 2 z comma 0. In that case, fz must be the integration of gamma 1 z0 minus I gamma 2 z0. And that means we are getting some actually form of it. On the other hand, if a harmonic function is known only, then we can write it as f dash z equal to vy plus ivx. So actually, these are the forms which are known from this relation, above relation. So f dash z equal to vy plus ivx. In that case, we can assume it some gamma 1 xy plus I gamma 2 xy. Now, if we are putting again x equal to z and y equal to 0, in that case, f dash z must be gamma 1 z0 plus I gamma 2 z0. And therefore, just by integrating it, we can our f. So this is the Milne-Thomson method. Now, power series and its radius of convergence. A power series with center z0 belongs to the set of complex numbers, and coefficient bi for I equal to 0, 1, 2, and so on is of the form summation n equal to 0 to infinity bn z minus z0 whole to the power n. That means it can be written as b0 plus b1 into z minus z0 plus b2 into z minus z0 whole square plus dot dot dot. So it is an infinite series, okay, with the coefficients bn. Now, radius of convergence, a power series summation n equal to 0 to infinity bn into z minus z0 whole to the power n has radius of convergence r greater than 0 if r is the supremum of rho greater than 0 such that the given series is convergent for all z belongs to B z not comma rho. That means this within this open ball B z not comma rho, which is defined as z belongs to C such that mod z minus z not is less than rho. So in this actually open ball, this series is everywhere convergent. Now, there is a theorem regarding this radius of convergence. If R is the radius of convergence of a power series base, summation Bn z minus z naught to the power n, then R is infinity implies the given power series is absolutely convergent for all z belongs to C and uniformly convergent in any bounded set. Okay. Absolutely convergent means just we have to consider the mod values of each and every term. So the next one is if 0 less than or less than infinity, this implies that the considered power series is absolutely convergent for all z belongs to C with mod z minus z not less than r, uniformly convergent in all z belongs to C, so that mod z minus z not less than equal to rho, where rho is less than strictly less than r, and divergent for all z belongs to C with mod z minus z not greater than r. So it is impossible to say that whether this series is convergent or divergent on the circle mod z minus z not equal to r. So if r equal to 0, it implies that the given power series is convergent only at z equal to 0, and the sum must be 0 in that case, and it is divergent for all z belongs to C minus z. So the next theorem, the function fz equal to summation b n z minus z naught whole to the power n, it is analytic within its radius of convergence. So if its radius of convergence is r, then within any ball b z naught comma rho, where rho is strictly less than r, in that case f is analytic bearing. So some properties of power series. So this is a theorem. So let f from the domain D to C be a function which is defined over a domain D, and for some z naught belongs to D, such that f is analytic in B z naught comma r. So this is an open ball with center z naught and radius r. Then for every z belongs to this open ball, f has a Taylor series expansion about z naught as the following. So fz is equal to summation n equal to 0 to infinity n z minus z naught whole to the power n. So where this an is equal to fn z naught by n factorial, which is the Taylor's actually coefficient in Taylor series expansion. So let us consider fz equal to sine z, where z belongs to C. Then f is analytic at z naught, and for all z belongs to C, this fz can be written as z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial, and so on. So this is the infinite Taylor series expansion for this fz equal to sine z. The conclusion: the concept of analyticity is advanced than the concept of differentiation. An analytic function has several vital properties. Number one, an analytic function is infinitely many times differentiable. There is no non-constant entire function which is bounded. The zeros of an analytic function are isolated, and the zero set of a non-constant analytic function cannot contain a limit point. Apart from all this, there are so many properties of analytic functions, so which we are not discussing here in. Thank you.